all, how do you read this? When you read this to me, read it like this. Log base b. That's like a subscript, not an exponent, which would be a superscript, but a subscript. It's log base b of x. You always take the log of something. In this particular case, we're taking the log of x with a base of b. So we read it log base b of x equals y. Does that make sense? So I'll insist as we start talking about this and you read things that you read it appropriately. Log base b of x equals y. Here's the good news. The base of the log is the base of your exponential form. They both have bases and they are the same thing, which is nice. But when you're taking the log form and you're going to exponential form, it's your base, and I'll constantly say this, raised to the other side. So this is going to be b raised to the y power equals x. Okay? That's your translation. Your base of your log raised to the other side equals x, and now it's in exponential form. So let's look down at exercise 2. They want us to evaluate these. Now, you have a log button on your calculator. Here's the problem, though. Your log button's right here. If you hit that, it doesn't give you a base. Okay? We're going to learn that this, when you just see a plain old log, it's technically log base 10. So to do log base a number other than 10, like log base 2, we're not going to be able to use that log button. So we have to translate. So we're trying to figure out what this equals. So I'll say equals question mark. And I'm going to translate it. Log base 2 of 8 equaling something is the same thing as the base of 2 raised to the other side, question mark, equals 8. So what's the value of this? 3. Log base 2 of 8 is 3. Got it? Nathan? You can. Absolutely. I just, throwing an X in there confuses some of your peers, so I wasn't going to do that. So, and sometimes I'll tell you this. This is like the little kid way of referring to logs, but sometimes people say, just for understanding purposes, they call this the what power function. Because what you're really asking yourself is the base of 4 to what power gives you 16? 4 to what power gives you 16? 2. So log base 4 of 16 is 2. 5 to what power gives you 625? 4. And you could check on your calculator. 5 to the 4th power equals 625. It's your base raised to the other side. Check to see if that equals what's kind of in the middle here. 10 to what power equals 100,000? Good? Here's a good one. 6 to what power equals 1 over 36? And we're a little bit better at that now because we saw some of that yesterday. Yeah, if you didn't know it was -2 right off the bat, you could obviously make this 6 to the -2 based on what we did yesterday, and then you know that x is -2. 2 to what power is 1/16? -4, great. 5 to what power is radical 5? 5 to what power is the same thing as radical 5? Yeah, this is piggybacking on your understanding that radicals are the same thing as fractional exponents. We're taking the square root of 5. So this is 5 to the 1/2 power. And this last one, I might write out 3 to what power equals, now how could I rewrite the cubed root of 9? 9 to the 1/3 power, right? And then go with what we learned yesterday. 9 is the same thing as 3 squared to the 1/3 power, which is 3 to the power to power means 2 times 1/3 is 2/3. So this whole thing, well, 3 to the question mark equals 3 to the 2/3 means this whole thing equals 2/3. That one's tough to do without work. Okay? So far so good? It's just a different language of exponents. Read this for me, Isaiah. Number 4. That's not how you're supposed to read it. Someone help him out. John, how do you read this? Right. Log base 3 of 40. You're taking the log of 40 with a base of 3. Log base 3 of 40. Okay? So, essentially, we're trying to figure out 3 to what power equals 40. Now, it's not going to work out exactly, is it? But they don't want it to. They're saying between what two integers must it lie? So, you kind of figure that 3 squared is 9. 3 to the 3rd is 27. 3 to the 4th is 81. So 40 would have been in there, right? So our exponent has to be between 3 and 4. Okay? The truth is the real answer there is a crazy, crazy decimal. And you'll never get it because it's 3.357762781 and it goes on forever. It's an irrational decimal. Could you guess and check to get to the nearest 10th? Yeah, you could do 3 to the 3.5. Too high or too low? Too high. 3 to the 3.4. Too high, right? 3 to the 3.3. So which one's the closer one to the nearest 10? 3.4 or 3.3? 3.4. But what if it asked you to round to the nearest 100th? So if I did 3 to the, that's 3.40, 3.45. Too high. Well, actually, right, 3.4 was too high. So anything 3.41 is going to be too high. So maybe I do 3.38. Oops, I accidentally hit a plus sign. That's a little too high. 3 to the 3.37. I mean, this game could go on. Guessing and checking isn't going to be the way to find the answer. There's got to be a way to find the exact value of x. We will get to it, but just not yet. Okay? This is where I tell you, if there is no base written, we assume the base is 10. So if you just see log of 100, that is technically log base 10 of 100. So 10 to what power is 100? 2. So this is where your calculator can be used. If I just type in log 100, it's going to give me 2 because it processes the base is 10 as well. This is log base 10 of 1 over 1,000. Without a calculator, what is that? -3. And this? Log base 10. So 10 to what power equals root 10? 1/2. And again, your calculator will do those for you. Okay? Flip to the back. Now, we have a paragraph. Logs are functions too. All right? before, I guess we'll get to the parent graph down below. Even though this is talking about a function and we don't know anything about the parent graph, we can still find the y-intercept. You can do that with any type of function, even if you've never seen it before, because to find the y-intercept, you plug in 0 for x. So we're just going to go y equals log base 2 of 0 plus 8 plus 9. That's going to be log base 2 of 8 plus 9. And order of operations says we're going to perform log base 2 of 8 first. What's that value? What's log base 2 of 8? 3. 2 to what power is 8? So that's 3 plus the 9 will give you a y-intercept of 12. Okay. I don't think I love the way this is organized down below. Here's what I'll start by telling you. We're going to find that logs are, and this are the same thing, so this is a log equation, technically, just translated. Logs are the inverses of exponentials, because our exponential equations were y equals b to the x, weren't they? That's your exponential parent graph, y equals b to the x. You see how your x's and y's have switched spots? Yes? Log graphs, which is why we couldn't write inverses the other day of exponentials, because in order to write the inverse of an exponential function, we have to switch the x's and y's and then solve for y. You don't know how to solve for y yet. You still don't know how to solve for y. It will require logs, okay? So we'll get there, but this particular exercise starts with an exponential parent graph with a base of 2, okay? Already there. We did that the other day. If we want to invert all, like this function, we need to invert all of these points, yes? We did talk the other day how exponential functions are one-to-one because they pass the horizontal line test. You still on board with that? Okay, so yes, passes horizontal line test. So based on your answer from part A, what must be true about the inverse of an exponential? It is a function 2. Because if the original passes the horizontal line test, then the inverse will pass the vertical line test, making it a function. Okay? So now we're going to plot this one's inverse just by flipping all of the points. So rather than negative 3 1/8, we're going to have 1/8 negative 3. 1/4 negative 2. 1/2 negative 1. You get the point. Fill all those in. This will be the inverse, which is going to be a log parent graph, what you're about to see here. So 1/8 negative 3 is barely off the y-axis down to negative 3. 1/4 is also barely off the y-axis, comma negative 2. 1/2 negative 1. 1 0. 2 1. 4 2. 8 3. Okay? What do you see in that picture that is always supposed to be true of inverses? Starts with an S, ends with imetry. Symmetry. Over the line, y equals x, that perfect diagonal line. Okay? So we have that feature going for us. Now part D says what would be the first step. So here's the exponential function. What would be the first step to finding an equation for an inverse? What is it? Nate? Did I say y-intercept? Yeah, what would be the first step to find an equation for an inverse? All inverses. First step's on the back of a flashcard. Switch the x's and the y's. So then, if we were writing the inverse to this exponential function, it would become that. X equals 2 to the y. And if you look on the front, that's what we have. X equals 2 to the y, it's just our base is 2, means the same thing going backwards as log base 2 of x equals y. I just took my translation rule and went backwards. So my base of my exponent was 2. That's the base of the log. It's always the base raised to the other side of the equal sign. So that's the 2 to the y equals x. You can definitely see it better if you look at the log and think backwards, right? But this and this are the same thing. So the inverse, y equals 2 to the x, or the inverse of y equals 2 to the x, is this graph, which is log base 2 of x. Y equals log base 2 of x. Any questions so far? So let's talk parent graphs. And I'm just going to do this. Y equals 2 to the x versus y equals log base 2 of x. When we were dealing with exponential equations the other day, what were our critical points? 0, 1, and 1, comma, b, which in this particular case happens to be 1, comma, 2. And what was the other critical feature of exponential functions? We have an asymptote, and where is that? The x-axis, which is technically y equals 0, right? So when we think about critical points of the inverse, what's going to happen? They flip-flop, right? So rather than 0, 1, we have 1, 0. Look at the graph we sketched above. Do you see how we have 1, 0? Yes? Instead of 1b, we're going to have b1, which in the case of when the base is 2, that's the point 2, 1. Look up at your graph of your log function. Do we have the point 2, 1? We do. Right up here, 2, 1. And asymptote. What's going to happen to the asymptote? Y equals 0 is going to become x equals 0. And if you look at it, you're never going to cross that axis. Because think about what's going to happen to your x values if you keep going with smaller here. -4, -5, -6. What's happening to these x values? Smaller and smaller and smaller, cutting in half, cutting in half, cutting in half, never going to reach 0. So our graph never reaches 0, and that's an asymptote. Do we follow? Okay. Let's talk domain and range again. For the exponential function, what was the domain? Look at it. -infinity to infinity. There is no restriction. We can plug in any x value that we want. But what is the range? The lowest this exponential graph ever gets is 0, but not including 0, so we use a parentheses to infinity. So let's look at your log graph. What is its domain? What's the furthest left this graph is ever going to go? 0, but not including 0 to infinity. And the range, negative infinity to infinity. What do you notice about the domains and ranges of these inverse functions? They flip-flopped, right? All x's become y's, all y's become x's. So your domains and ranges change. What's your y-intercept of this graph? 1, and that becomes the x-intercept of this graph. What's your x-intercept of this graph? Does not exist. So guess what doesn't exist here? Y-intercept. All things flip-flopped. This brings up the domain here of a log function, brings up a great point. Your domain has to be anything greater than 0, which means you can never take the log of a negative. Watch what happens on my calculator. Log of negative 5. Error. Even the log of 0. Error. Because you can only take the log of positive numbers. Think about this. If I did log base 2 of negative 3 equals what? From a translation standpoint, that would be 2 to what power equals negative 3. Never going to happen with your base being a positive number. Because a positive raised to anything is going to stay positive. Yes? So you cannot take the log of a negative. And also, what did we talk about? Your bases always have to be greater than 0, right? Your bases here always have to be greater than 0 as well. Your bases, whether it's a log base or an exponent base for functions, have to be greater than 0. No one will ever ask you to graph negative 5 in parentheses to the x power. Okay? No one will ever ask you to graph log base negative 5 of x. Can't do it. Okay? And the last thing, let's now go back to this one. This one had a parent graph of log base 2 of x. What? And think about your critical points. 1, 0 and 2, 1. Right? 1, 0 and b comma 1. That's our parent graph of this. What transformation happened? Because we have no y-intercept initially. But what transformation happens first? Andrew. Left 8 units. Correct. So this 1, 0 is going to move way over here. This 2, 1 is going to move way over here. So left 8 units is going to do this. That'll make negative 7, 0 and negative 6, 1. So look at where my y-intercept is. It's a little bit further up, right? If this is negative 8, 1, yes, it maybe is in the like 3, 2, 3, 4 range-ish, just guesstimating. And then what is the next transformation, Maggie? Up 9. So wherever that was, whether it was at 2 or 3 or 4, is now getting shifted up 9. So I know that my y-intercept is definitely bigger than 9, which, what did we find it was? 12. Does that make sense? Okay, so there's also the whole transformation piece. Now, you can have a parent graph. Remember how your parent graph of exponentials, y equals 2 to the x could be a parent graph, y equals 3 to the x could be a parent graph, right? With critical points, both 0, 1, but this one had 1, 2, and this one had 1, 3. And you could change the base, and they all have their own parent graph. Same is true for logs. Log base 2 of x, that's the parent graph. Y equals log base 3 of x. This is also the parent graph with 1, 0, but rather than having 2, 1, it's going to have 3, 1. It's b comma 1 is your second point. So your bases can kind of change up, but every parent graph will have this structure. Okay? So if we're jumping to critical basic facts to know, we have 2 to add to our list today. 1 is the translation, translate log base b of x equals y. And you need to translate that to b to the y equals x. That's issue 1. Okay? Issue 2 is the log base b of x parent graph, which is looking like this. I'll know what your asymptote is because you won't cross it. This has to be labeled 1, 0, and then your next point is b comma 1. Okay, it's really the exponential parent graph switched. Okie doke. I feel like I wanted to say one more thing. I did. If someone asks you, well, I guess I don't necessarily know if I need to do it. If someone asks you to plot log base 5 of x using a table of values, here's the difference. If I translate this, what does this translate to, Evan? Nope. Someone help him out. Mason. Right. 5, the base of 5 raised to the other side y, so 5 to the y equals x. Here's the thing about this kind of table of values. This and this are the same thing. I'm not going to choose my x's and calculate y. I'm actually going to choose my y's, -2, -1, 0, and do 5 to the negative second power, 1/25. 5 to the negative first power, 1/5. It actually kind of flips around how you would choose your table of values. Does that make sense? Maybe a little bit. Truth is, you shouldn't have to do a table of values because if you know your paragraph has 1, 0 and b comma 1, then you're fine. It has 1, 0 and 5, 1 here, and then you just know the general shape, so you can plot.